Good morning, class. Well, morning for me. It's 6:31, February 9th, 2019, and we missed a whole week of school because of the snow and because of Faculty Development Day. This is the lecture series. I'm going to make this a series of short videos instead of one long one, and I'll be posting them to modules for week 6 because week 6 we missed all week because February 5th we had a snow day. And February 7th, we had Faculty Development Day, and it's likely we will miss Tuesday as well, but stay tuned for that. I'll send out an email. Make sure you continue to check Canvas and emails. It's beneficial to you. So, what are we talking about? We're talking about imaginary numbers. We're introducing a new concept. If you if you have a TI-36X Pro, if you look at the pi key and you press it 3 times, a number will come up, a letter will come up. It's called I. The letter I will come up if you press the pi key 3 times. If you have a different type of calculator, we can talk about this in class. But that's how you bring up the I key on your calculator, at least for the 36X Pro. Now, what does I stand for? I stands for imaginary numbers. Imaginary numbers, well, what does I stand for? It stands for a number. It stands for this number right here. Square root of -1. We're going to explain how that is relevant to us and what we've already been doing with it, because graphing on two-dimensional graphing where you have an x and y coordinate is not really doable. It doesn't make any sort of sense without the letter I. So I stands for the y coordinate, but that's something we'll get to shortly here. But just know for now, you can find I on your calculator by pressing the pi key 3 times, or and also that I stands for the square root of -1. Those are the two things to take away for right now. Next slide. And there will be short pauses between slides because I'm recording each section for each slide, so there might be some odd transitions, but that's just how I'm going to do it. So just some slides I won't mention a whole lot on. I encourage you to read this and kind of absorb what they have to say here. But for this specific example right here, that's 5 plus 2i. So that's 5 to the right on the x-axis, plus 2i would be up 2 on the y-axis. So just know when we're talking about complex numbers, and complex numbers is this and this, if you have two parts. An imaginary number is only this. That's an imaginary number. Complex numbers are in 2 dimensions, and they have an x and a y coordinate. And how we've been writing this prior to now is 5, 2. They are the same thing. So here's another nice visual here. We have real numbers on the left. As we've been seeing, pi is a real number. It just goes on and on and on. The square root of -15 is a real number. -2 is a real number. 1 is a real number. 5 is a real number. On the right, we have pure imaginary numbers, which are expressed in terms of I without an x coordinate. Now, complex numbers, which is what we're mostly interested in this class, gives us an x and a y coordinate. So written how we have been writing it recently is 3, 2. Now if this right here, if this was a minus sign, you would know that 2 would be 3, -2. But that's for later. So we have already been dealing with numbers on the imaginary axis. So if we hadn't, they would just be on the number line. This is the real axis, the x-axis. But as soon as we add in terms of y, we can now graph in 2 dimensions, which is much more interesting and valuable in mathematics. So we will learn to, in this section, add and subtract complex numbers and multiply and divide complex numbers. So if we were to graph 3 minus 4i, we would go over to the right 3 on the x-axis and down 4 on the y-axis. Like I said earlier, this minus sign shows that we are on the negative side of the y-axis. So, multiplying imaginary numbers. So we have two binomials, and FOIL still works. So first we do 2 times 2 gives us 4. Then that's first. Then we have outside, we have 2 times negative 5j will give us negative 10j. And then we have inner next. The 5j times 2 will give us positive 10j. And then last, we have 5j times negative 5j, which will give us negative 25j squared. Now, these terms will cancel because they're like terms. We have a positive 10j and a negative 10j. So what we're left with is 4 and negative 25j squared. Now, j squared is this, negative 1, square root of negative 1 squared. And we know that these terms will cancel, and we're left with negative 1. And that will go back to your rules of exponents, because if you remember, the square root of the square root means to the 1/2 power. So if we're squaring the 1/2 power, it will equal the power of 1. So that's how we get rid of the square root by squaring. And that's why we're left with negative 1 times negative 25 right here. And so then you will just add 4 to 25, and that will equal 29. So this whole term, we'll be able to simplify it to that right there, 29. Those are the steps. And if you need to review certain sections of this video again, that's fine. That's why this is a good tool, good learning tool. So I'm not going to talk too much about it in this slide, but take note of this over here up in the upper right hand corner. If you have a j to the first power, you're left with j, and I'm using j now instead of I, because in electronics I is also used for current. So in electronics we use j. It looks like an I, but we just kind of curve it off to the left instead. So when you see j, know that it's the same as I. It's just a different symbol for it. So j to the first power is j. J to the second power equals this negative 1 that we came up with, and that's how we were able to take the negative 25j squared and simplify it to negative 1, is just because that is the general rule. And a j to the third power equals negative j, while j to the fourth equals 1. As stated earlier, some slides I won't spend much time on. Some slides I might not narrate at all. I'll just let you review them yourself. But take note that this is referencing page 111 if you want further explanation and examples, and also the pages that follow that will give you good examples for what we're talking about here. So back to a previous rule of regarding exponents, and in this case, more specifically the square root, which is anything to the 1/2 power. And if we have, so as an example, so the square root of a times b. If we're given a number, it doesn't have to be shown as a times b. It can be shown as the square root of negative 25. And we want to get the negative. We want to isolate the negative 1 because we want to express this in terms of I. So that'll simplify to the square root of negative 1 times the square root of, not negative 25, excuse me, square root of 25. So from there we know square root of 25, and if you don't know this, you can plug it into your calculator, find out if it squares out perfectly, which it does, which is why I chose this as an easy example. So square root of 25 is 5. So that negative 25, square root of negative 25 will simplify to 5 times negative square root of negative 1, or preferably 5j. You can write it as 5j or 5i in this class, but we're gonna use them interchangeably. J and I are the same thing. It's just a different way to express it in electronics. We typically use J because I, like I said earlier, is substituted for current. So, what do we do with a number different than 25? Because 25 can simplify to 5. The square root of 25 can simplify to 5, and we've shown you how to isolate the negative sign to come up with the letter I instead of squaring a negative number, because that's irrational. So, yeah, here's another. This is what we want to do. It's another way to write what I wrote on the previous slide, which was the square root of negative 1 times the square root of 25. In this case, they leave them both under the same square root, which is also fine. But we definitely want to isolate that negative 1, and remember that that stands for I. So we now get to factoring. So we want to factor two numbers under the radical, and we want one of them to be a perfect square. And what I mean by that is the only one on that list that is a perfect square. 3 times 3 equals 9, so we can factor out a 9 from underneath the radical, because neither of those is a perfect square, neither of those is a perfect square. The next biggest one is 5 times 9 equals 45, and 9 is a perfect square. So we can write it like square root of negative 1 times the square root of 5 times the square root of 9, and that will simplify to 3 times 5j, or I. However you choose to write it is fine. But if you're going on to electronics, I encourage you to write it as j and not I. So this is essentially what we just did. And yeah, so the negative 45 simplifies to the square root of negative 1 times 45. Then we have the square root of negative 1 times 9 times 5. Rewritten like this, as we already done. This simplifies to 3, but it's still multiplied by the other two terms. So we have 3 times the square root of 5j. So if you refer to page 113, it talks a little bit about adding and subtracting complex numbers. So you add the real parts, which is in this case the 3 and the 2, which will be 5. And then you add the imaginary parts, which will be negative 4i, or j, plus 5i. And so then we'll have 5 plus I. And I guess we'll just leave it as I. I like writing i's better than j's. So, but remember, in electronics, j means the same thing. This will be one of the slides that I'm not going to talk much about, but because we just covered it. And moving on. Now here's an example subtracting two complex numbers. So when I say complex numbers, this whole term, both terms are required for it to be a complex number. This is the imaginary part, this is the real part. Added together or subtracted in some case, they equal a complex number. So we have negative 5 minus negative 11 will give us a positive 6, and then a positive 7i minus 2i will give us, the remainder is 5i. So this whole term simplifies to that. and that is subtracting complex numbers. So next we have multiplying complex numbers, which is just like multiplying regular numbers, except one of the terms you include I. So you have 3 times 6 equals 18, and 3 times 2i equals 6i. No real tricks here. This is just regular multiplication. So I'm not going to go through this specific term because it doesn't give me real numbers, but it would just be like FOIL, and you do the first, the outside, then the inside, and then the last, which looks like that. So next we have multiplying two complex numbers. So we do 2 times 2 equals 4. Because FOIL still works first. Then outside is 2 times negative 5j equals negative 10j. And we have 5j, positive 5j times positive 2 equals positive 10j. And then you have a positive 10j times a negative 5j, positive 5j times a negative 5j equals negative 25j squared. Now, later on, shortly, we'll go more in depth on how to simplify terms of j, because j squared is negative 1, as you remember earlier. So essentially, you're left over with a 4 minus 25j squared. Well, j squared is negative 1, so you're left over with 4 plus 25 equals 29. That's what you're left over with. Because, going back to this step, if you have a negative 25 times a negative 1, which is what j squared is, you'll be left with a positive 25. And you can just add those terms together because they're both real numbers. This is pretty much exactly what we just talked about, so I'm not going to spend much time on it. I'm just going to move to the next slide. So we talked a couple times about when you have j squared, it equals square root of negative 1 squared, which is just negative 1. Well, these are the other possibilities, and it can go beyond j to the 4th power, but it's just a repeating cycle. So j equals j squared equals negative 1, j to the 3rd equals j squared times j, so essentially negative 1 times j equals negative j, and j to the 4th equals j squared times j squared, which means negative 1 times negative 1 equals 1. Because a negative times a negative will always equal a positive, and both numbers are 1. So the cycle just repeats beyond 4. So j to the 5th will be just like j to the 1st, as will j to the 6th be like j squared, j to the 7th will be like j to the 3rd, and j to the 8th will be like j to the 4th. And it will repeat, at 9, so j to the 9th will be just like j to the 1st. So here's where it gets a little bit more complicated. Dividing complex numbers. So I would refer to page 115 to follow on for this next part, because it does get a little bit complex. Pardon the pun. So, the complex conjugate. The complex conjugate is if you were to multiply. So if you had, well, for a specific example, let's just go to the next slide because I know they give me one, and let's work off their example. because we have more space. I don't have a whole lot of space to write on these slides. So to divide C plus DI, well, let's do this with real numbers again. Sorry, like I said, some slides are going to be pretty quick, but I'm going to leave at least some narration just so you can have time to review it and pause the video if you want to review that particular side a little more. But I want to do division with real numbers. So moving on. So I will talk about this slide just briefly. This is going back off the previous example. So the complex conjugate is this guy right here. This was our original term. To get this, and I still don't like doing this with not real numbers because it's just going to end up awkward. It's much easier to see with real numbers, but so to get rid of the I in this term, you multiply by the complex conjugate, which is this, but then you also have to put the complex conjugate in the numerator so that it's essentially the same value. The number values are the same. If you were to, it's just like multiplying by 1 over 1. I mean, yeah, that's what it would be akin to. Again, we're still dealing with letters, which I feel like overcomplicates the issue. Just hang tight here. We'll do this with real numbers in just a moment. So now we get to deal with some real numbers, which is great. So we multiply by the complex conjugate, which is 4 plus I in the denominator, which we also have to put the same thing in the numerator for all things to be equal, which is 4 plus I, and then we start multiplying. So I'm going to do the denominator first. We have 4 times 4 equals 16 plus 4I minus 4I minus I squared. Next, on the top, we have 8. Then we have plus 2I plus 20I. And then we have 5I times I equals positive 5I squared. Just carry on the little line. And now we'll simplify things, and the positive 4 and the negative 4 cancel out to 0. And then we have 16 minus negative 1, because I squared is negative 1. And so that'll simplify to 17, but we'll bring that over to the next step. And we have 8 plus 22I, and we have plus 5I squared, which we'll do like this. Oops. Not what I wanted to do. Plus 5 times I squared is negative 1, which we'll just write as negative 5. So we'll write the final answer in the upper left hand corner, and we'll simplify like terms again. Actually, we just know that the only like terms we have left to simplify is the positive 8 and the negative 5, which is 3. We know 17 is going to be the entire denominator, and we have 3 plus, I didn't give myself enough space. I'm not going to redo this whole video, so we'll do some erasing. So in the denominator, we have 17, and we have 3, and then we have plus 22I. That will simplify to 3 over 17 plus 22 over 17I. So that's actually a coordinate on the XY plane. And that's an important takeaway from all this. It wouldn't be a very easy place to draw, but you know, that's a place on the XY coordinate. The X is your 3 over 17, your Y is the 22 over 17. This is just exactly what we just did. It's just showing you the work again. So we'll move on to the next step. And here's the final answer. Yes, we did it right. They are the same answers. Great. Well, that's the end of the introduction to imaginary numbers and complex numbers. We'll be dealing with those a lot for the rest of the course. I mean, not exclusively, but it's definitely a common theme, so you want to get to understand them and be able to manipulate them very well. So next is quadratic equations, and I will be crafting that video shortly. I hope this was informative for you. Feel free to go back and watch it again, or give me feedback or questions over email if you wish to. I was thinking about maybe opening a discussion board. We'll see. Okay. Yeah, but we've gotta keep chugging along even though we're missing class days. So I hope you guys keep that in mind and keep working on homework.